Good morning, everyone. Thank you, Thomas, for introducing me. Today's presentation from the side of TU Delft will be delivered by me and my colleague Vaso Repa. I'm a postdoctoral researcher in Delft University of Technology, and Vaso is my colleague and also an associate professor in TU Delft. So I can share my screen, and Vaso can start. Okay, Vaso, please go ahead.
I don't see no. Yes, now
Okay.
I see the presentation. Can you please, Nikos, thank you, change the slide? So, as Nico said, I'm associate professor at the Delft University of Technology. And today we are going to discuss in the next 25 minutes about how we make short sea and inland waterway transport intelligent, rule compliant, and fault tolerant. So safety is the core of our research, the research of SafeNet Group, which is part of the Maritime and Transport Technology Department at Delft University of Technology and part of the research lab Autonomous Shipping. So we consider that safety goes hand in hand with autonomy and intelligence. And what we do as a group is that we design both vessels and infrastructure, transport infrastructure like locks, which is very a typical infrastructure for inland waterway. We make them intelligent in order to enhance the efficiency of the transport, but of course in the core is the safety. So how to handle abnormal events, as you can see in this visualization, where a ship is experiencing a fault, an engine fault. So how can we handle this abnormal event, not only on board the vessel, but also considering the whole network? And here we have the inland waterway network. So we will hear first Nikos describing how we make these systems intelligent and rule compliant, because we acknowledge that these maritime transport, short sea and inland waterways are governed by rules. And then I'm going to talk about fault tolerance. Nikos, the floor is yours.
Thank you, Vaso. As mentioned, our group is mainly occupied with safety aspects, and safety is actually a really important thing both for conventional vessels because we have a lot of regulations that like make sure that we have the safety in the first place. But in the case where we have autonomous vessels, it's also very relevant because in this case we would need a lot of cyber devices but also intelligent algorithms in order to ensure that we have the safety in autonomous operations. So, for example, in this figure, you can see in figure B, you can see that now we're talking of having remote operation centers that are going to communicate with autonomous vessels. Then we can have some other conventional vessels that monitor how this autonomy goes on. But also we have the port areas and the inland waterways. So the interactions of the autonomous vessels with the infrastructure is also a very interesting problem to consider. The main actor, let's say, in all of this is the guidance, navigation, and control system. And this is the most safety critical system also for autonomous vessels. It's comprised by three systems. First of all, we have the guidance, and guidance essentially provides the necessary course, speed, and power in order to achieve the mission objective. So, in a way, it plans ahead to take care of the objectives of the mission. To do so, we need to consider some objectives, like, for example, collision avoidance, where a safe path or a safe speed would need to be implemented. Uh, we also have the navigation system, and the navigation system is mainly composed of sensors that has to do with the situational awareness of the vessel, sensors that have to do with state estimation, but also sensors that have to do with how the vessel perceives its environment, surrounding environment. Last but not least, we have the control system, and the control system implements the planning of the guidance. So it computes the signals to the actuators to make the system achieve the desired behavior. In all of these, in both of the three systems, guidance and navigation and control, we can also include fault diagnosis and fault tolerant capabilities, which we will talk later on in our presentation. Now, there are a lot of papers in literature that discuss GNC systems, but still we find that some things are missing from literature and need to be investigated further in order to ensure safety of autonomous vessels. First of all, although we have papers talking about navigation in open sea, in inland waterways, but also in short sea areas, there is a small selection of papers that discuss operation in a multi-environment situation. So when the vessel transit, for example, from short sea operation to inland waterway operation. This is really important because we would have a change in the physical constraints like the boundaries of the waterway or the depth of the waterway, which would in effect change the dynamics of the operation. The second aspect that's really important is the rule awareness. And in most of the literature till now, only international regulations like call regs are treated. And call regs, they are really important. They are applicable in short sea, but also the open sea areas. But in case we go into inland waterways, we have more regional traffic regulations that are not, let's say, taking as much of a spotlight. And these regulations are important for the guidance in order to provide a path that doesn't only avoid collision, but is also compliant to the traffic regulations. The third aspect is what kind of collision cases we're investigating. So we can have collisions that are between different vessels, so these vessel-to-vessel collisions, V2V in short, but we can also have collisions like vessel-to-infrastructure, V2I collisions. In this figure, you see an incident that happened a few years back. I think it was 2024. This is the Baltimore Bridge incident in the US, where a vessel collided with a bridge because of an engine failure. Not appropriate action was taken to avoid this collision, so we need to also consider this kind of events. Last but not least, uh, although there is a lot of literature that discusses collision avoidance and also intelligent guidance using, let's say, the states of the system, the sensor inaccuracies are not so much discussed. And by sensor inaccuracies, I mean faults, but also the sensor noise. And we need to consider those because we need to certify that we can follow the path, the necessary path, as precisely as possible. So, zooming in into our project Seamless and following this motivation, the objective is to design a guidance, navigation, and control scheme that is adaptive to both short sea and inland waterways, that each of them is associated with different disturbances, but also different physical constraints. Then to be safe against physical, but also cyber threats like static obstacles, grounding factors, but also faults from the cyber aspect. We need the GNC to be compliant to various collision avoidance regulations and to intelligently switch between applicable regulation when required to do so. And finally, we need to be fault tolerant against both sensor and actuator faults. In our group, we are mainly using models and we are developing model-based approaches for all the different aspects of the GNC system. And in this case, you see the model that we are using for Seamless. And this is based on the Maritime modeling group. And we chose this model because it has advantages over its inherent modularity. So, for example, you see in this equation that we have the forces. Here are the hull search forces, the propeller search forces, and the rudder search forces. But in case, for example, we want to consider bank effects as well, which we will do so in the inland waterway environment, we can just have an additive term here plus xb, for instance. The same for the other degrees of freedom. We have six different states, mainly the velocities of the vessels in the surge, sway, and yaw degrees of freedom. And also we have two positions, X and Y. Uh, and finally, we have the heading of the vessel. And this system is transformed into state space format that's more suitable for control applications. In order to deal with sensor inaccuracies, first we need to model these inaccuracies. So we do so like this. We have the measurements, Y, and the measurements are dependent on the states. Here we assume that we don't have full knowledge of the states of the system. So we only have knowledge of the positions of the vessels in the X and Y direction. We have the heading of the vessel, but we don't have specific information on the velocity of the vessel in the different degrees of freedom. What we can have, for instance, is the speed over ground, which can be given by the AIS system. To these states, let's say to the observable states, we add a noise vector D, and this is generally random, but we assume that we know its bounds. And finally, we have the faults, and we will talk later about these faults in the presentation. Aside from quantitative approaches, we also have qualitative approaches like the one you see in this slide. So in our case, we're discussing of having a semantic database in order to allow for the intelligent functions that we want to implement. So the database is comprised by smaller databases. Here you see, for example, we have a small database or class of the vessel design, where we might store the different characteristics of the vessel, like the particulars, the name of the vessel, but also certain specifications that are consider the vessel itself, for example, the rudder limitations. Then we have a class that talks about vessel sensors. And in this case, we can, for example, store the sensor name, but also the noise level of the sensor. This is actually tied to the assumption that we know the bounds of the noise vector. Then another class can be the operational environment, where we can store, for example, information about the significant wave height, the current speed, and anything that has to do with the environment, the weight of the waterway. This can also be done. And finally, we have a class that talks about traffic rules. And traffic rules, like Tolerant and VPR, they are by nature qualitative, meaning that they are a piece of text. So aside from the text, we can also include other parameters, like, for example, a switching value to say where the regulation is active or not. In order to implement this database, we use an open source software called Protege. And you see here what it looks like. We have the classes, what I just presented in the previous slide. And each class has one or more instances. In the case of regulations, instances can be different articles of Colerex or different articles of VPR. Then we have a short description, what this rule is about. And this is for tracing back, okay, what was the action that was expected by the regulations. And then we have two more windows, one considering class information. This has to do with which class the instance belongs to, but also which kind of dependencies it has. And the exact dependencies, like the methods that the instance uses, but also the variables of the instance, are stored in this window. So if the regulation is active, there's this variable reg active that goes to 1 when it is active. This semantic database is really important when we need to perform decisions. For example, considering collision avoidance in the guidance system of the vessel. So we design this semantic reasoner that has as inputs the database. This is populated offline, but also we can have some online aspects like the measurements of the own vessel, positions and heading, and the measurements of the other vessels that are interacting with our vessel inside the waterway environment, which can, for instance, be communicated through the VTA system. An important aspect to see whether we should take action to avoid collision is to see which traffic rule we are assuming depending on the situation, on the relevant situation. And we have three different traffic rules. We have the stand-on situation where we just follow our original course. We have the give-way situation where we need to uh, take appropriate action to avoid the collision. And we also have an emergency give-way, which means that we are stand-on, but we see that the other vessel is not compliant to the rules. So in this case, even though the regulations would not require us to take action, we are required to take action to actually avoid the collision. Uh, the output of the semantic reasoner are the deviations from the original path, and these are calculated at a specific time interval, uh, and steer the vessel away from danger, away from the risk of collision. Instead of generating only one trajectory deviation, so one tuple of delta x ref and delta y ref, we are generating an envelope, a collision-free envelope, and this is done for both inland waterways, but also short sea operations. Here, what you can see what I mean by collision-free envelopes. So suppose that we have a situation where in an inland waterway, our own vessel is the blue one, and the green vessel is the other vessel that is coming from the opposite direction. In this case, we would need to avoid the green vessel. So we would need to modify our waypoints. Let's say that we were going like this. We need to modify our waypoints in order to be at least below a certain limit, the green line that you see here. This has to do with the safety distance from the green vessel. So if we are below this line, then we are safe from the green vessel. But since this is an inland waterway environment and we're also considering the infrastructure, we cannot steer too far away from the green line because then we would collide with the banks of the waterway. In this case, we also specify another limit, and this has to do with the safe lane distance, so the safe distance from the boundary. Um, so in this case, we are allowed to modify our waypoints to be between the green line and the purple lines. It might be that our envelope only has one boundary, as can happen, for example, in the short sea situation, where we have again the blue vessel, our own vessel, and the green vessel coming in the opposite direction. But here we have no boundary on the other side. So all of the trajectories that are below this green line, they can avoid the collision with the green vessel.
Nico,
Yeah.
considering the time, I would suggest maybe to show the simulator and explain there maybe, or select some slides, please. Okay?
Yeah. Maybe I can show the simulator. I will just say this, that in order to find the role, the traffic role that our vessel needs to assume, we use this modular finite state machine. And here we have a classification of the different encounter situations with the specific role, the three roles that I mentioned, and also which situations correspond to each role. This is for Colrex, but we all can also have the same for BPR. And the BPR, we have different regulations. For instance, in the head-on, the vessel that is not following the starboard side of the waterway should give way to the other vessel. Whereas in the Colrex situation, both vessels need to take action to avoid the collision, so they are both give way. For the crossing situation, the vessel that's not following the starboard side shall again be the one to give way according to BPR. But in the case of Colrex, it has more to do with in which direction the other vessel is coming from. So if the other vessel is coming from the starboard direction, then we need to give way to that vessel. So we can also make the other branch, and we decide which branch based on the applicable traffic regulation. So to show you a small example, we are using this case study with an barge vessel, a pusher barge vessel. This is our own vessel, the blue one, and the green vessel is the other one. You can see that the trajectories, they are calculated, so the trajectory deviations are calculated, and the blue and the green vessel take appropriate action to pass each other port to port. Then this situation is resolved, and we go into the inland situation. So here we have BPR. The purple vessel is not moving to the starboard bank, so it needs to be the one to take action, whereas the blue vessel moves along the starboard bank, so it doesn't take appropriate action, and this is how we resolve the situation. Yeah. So all of this is good when we are not considering faults, but it's also interesting to see how the situations will change in case we have sensor, but also actuator faults. And in this case, I would like to call Vaso to the floor again in order to talk about the fault tolerant capabilities that we are implementing in Seamless. Thank you.
Thank you, Nikos. Could you please? Yes, thank you very much. So now in the next slides, I'm going to discuss how we design systems to become fault tolerant. And when we say fault tolerance, it's a two-step approach. First, we diagnose faults, and then we take actions in order to compensate for the fault effect. In the context of Seamless, we consider two types, thruster faults, and later I will talk about also sensor faults. What you see here on the left are some azimuth thrusters that we are considering that are in the back of the vessel. And as Nikos mentioned, in our group, we are using models, and we model the impact of a thruster fault in the motion of the vessel, as you can see here. So this model, this differential model, is the maneuvering model that Nikos presented, but this vector theta represents loss of effectiveness, which may stem from a fault in the power and propulsion system of the vessel. So the vessel does not give enough power thrust to the actuators to take the moves. Nikos, could you please change? Yes, thank you. So this is the overall scheme that we propose, and with this scheme, which is based on the GNC, guidance, navigation, and control, we enhance the GNC with rule compliance and fault diagnosis capabilities. In the center is the trajectory optimizer, that we are using model predictive techniques. We want to be proactive in collision avoidance, but also considering constraints like physical constraints. But of course, the novelty here is the fault diagnosis, where we detect that there is loss of effectiveness of the thrusters with this box, the fault diagnosis box. And the outcome is when it happened, and when it happens, we estimate the severity of the loss, and we fed back this to the trajectory optimizer, because we need to know how severe is the fault in order to take the appropriate action. Next slide, please. Okay, so here, this is an overview of the fault diagnosis step, two-step approach, detection the beginning, isolation later. So in this scheme, the diagram, what you see, theta 1 and theta 2, represents loss of effectiveness of the two thrusters in the back. And there are two sets, two schemes, what you see, convex sets. The red one describes the observed behavior, what is happening now. The blue one describes the expected behavior. So we expect that the values of theta 1, theta 2 are in the blue, and the red one is the current situation. So under healthy conditions, we expect that these two sets overlap, but when there is no intersection, we raise an alarm, the computer as a matter of fact, because everything is programmed, and there are algorithms with data that are executed, and we are saying that we have a fault when there is no intersection. And also we are using the projection of these sets in order to isolate, to find is the fault in the right thruster or in the left thruster. Nikos, could you please change? Yes, thank you. So I briefly discussed how we handle thruster faults, diagnosis and tolerance. And now I'm going to talk about multiple sensor faults. So it becomes very important that we assess and we check the health of the navigational sensors, which are necessary for doing everything, for all maneuvering actions. And what we consider, we consider the classic type of sensors used in inland waterway, like GNSS measuring the position, gyroscope measuring the heading, accelerometer measuring velocities like an IMU, the inertial measurement unit. And the goal, what we design is method to isolate multiple faults. And how we do it, Nikos, could you please? Yes, thank you. So this is a scheme. The green boxes are groups of sensors. So we have a set of sensors, but we are grouping them because this facilitates the isolation. So for each group, we design a monitoring agent with the goal to assess the condition, the health of the group, the sensors in the subgroup. And how we do it, as we mentioned, we are using model-based techniques. So this O describes, corresponds to an observer, which estimates the position, the heading, and also the velocities of the vessel. This is just an example. We designed several observers to estimate the motion of the vessel. Then the next part is the fault detector. Again, the diagnosis starts with comparing the observed behavior from the sensors, output of the sensors, and the expected. So this is called residuals. And Nikos, could you please change the slide? So here, in the first inequality describes an analytical redundancy relations where we compare the deviation from of the observed from the expected to an adaptive threshold. When this is not satisfied, then we raise an alarm. There is the detection of multiple fault in one detector. Could you please change the slide? Yes, this is the observer. So the output of its monitoring agent is a decision function, D1. And we collect this A means that this is an aggregation module that collects the decisions of the monitoring agents. And in this module, we create this fault signature matrix where the rows correspond to the decision-making process of every agent. That's why we see 4, for example. And the columns correspond to single and combinations of sensor faults. And 1 means that we have the monitoring agent is sensitive, very sensitive to this fault. Star means weak sensitivity, 0 means 0 sensitivity. In real time, at every time instant, what we do is that we compare the observed pattern to every column of this matrix, which is a way to do combinatorial, to apply combinatorial logic and then diagnostic reasoning. Nikos, could you please? Yes. So up to now, I described how to diagnose multiple sensor faults, but then when we diagnose by the set of monitoring agents, you see here the block, the next step is that we need to compensate for these effects. So in our group, we focus on designing virtual sensors, And in the context of this GNC scheme, guidance, navigation, and control, what we do is that we integrate the adaptive line of sight algorithm, a typical algorithm that offers drift compensation with virtual sensors. How we do it? Nikos, could you please present all the parts in this slide? Also
Yes.
the boxes?
Yes.
No. I will do it. I mean, I need to see the
Yeah, yeah.
full slide. So these are, you see, a complicated model, but I will describe the rationale behind this model. So with X, X hat is the estimation of the position of the heading and the velocities of the vessel. But at the same time, we estimate the drift, the slip angle. It's the uncertainty part. On top of that, we estimate the fault of the sensors. F hat corresponds to the estimation of the fault. So we managed to design virtual sensors that at the same time offers estimation of the state of the vessel, of the uncertainties, the slip angle, and the fault. And with this slide, we conclude our presentation about intelligence, rule compliance, and fault tolerance. Thank you very much, and we are happy to address your questions. Thank you.